Yeah, thank you. So I'm presenting the company Sourced. It's a company based in Madrid, Spain. And the current business model is that we choose the awesomest software engineers and match them to the best job offerings for them. And we do this not the way other recruiting agencies do. We take their source code, we analyze it properly, and have really good matches. The plan of my presentation is as follows. Well, first of all, let me remind you that here is a QR code. You can scan it and use this presentation entirely online. It's basically HTML, or go to the link on the bottom of this QR code. The plan of my presentation is as follows. First, I'll give some details about who we are and what we do. Then I'll cover, I think, the most important topic, how we extract features from the source code. Next, I'll present the deep neural network we use to extract some features from the source code. Present the results, and if you have time, I'll cover some related work. Let's start. So we believe at Source that everything is better with clusters. It's like Sheldon Cooper says that everything is better with Bluetooth, and we say that everything is better with clusters. Because if we are able to find groups of software engineers, we can match these groups to best offerings. We can group like junior people, senior people, divide them by different software ecosystems, whatever. And this is like our ultimate goal, and we try to reach it by several ways. Well, analyzing source code with machine learning techniques is not something very widespread. I don't think there are a lot of scientific articles about the topic. So everybody is used to applying machine learning to solving some marketing tasks, to solving science tasks, but, well, nobody actually tried to use deep neural networks to analyze the source code. And this is what we actually try to do. So we don't take a sales history, we don't take some ordinary features. We try to use the product of software engineers' work. What sources of features we can use? There are quite a few. First of all, we can use social networks, such as LinkedIn, Facebook, whatever sites. I don't know, personal homepages, blogs. It's a good source of information, but there are some issues with it. The main issue is that we cannot validate it. So we cannot guarantee that everything which the developer writes about himself or herself is actually correct. We can use version control stats. It's what GitHub shows you if you click the contributions statistics page. So it's how much did you commit every day, what's the history of your commits within several years, how are you productive. We can add some NLP processing of your commit messages as well. And this is also a good source of information, but I think it's not the main one. And the main one is the source code. We can divide this group into 3 subgroups. The first is algorithms, so basically what you try to code. The second one is dependency graph. It means that, well, nowadays, if you start a project, you're very unlikely to do it completely from scratch. You're likely to use some already existing libraries, frameworks, and these frameworks use some lower-level libraries, and ultimately, it gives you some nice dependency graph. There are a lot of startups focusing exactly on this subgroup. Namely, I think it's source graph and some continuous integration system which bases on entirely reviewing your dependencies. The third subgroup is style, source code style. It's interesting because we believe that if you tend to be consistent in your source code styling, if you code short functions, you have good function names, class names, you place good commands in the right places, you're likely to be better and more professional than people which don't follow these best practices. And let's focus on this last subgroup, on source code style, and see what we can do with features based on source code style. Let's play with some toy task. Let's try to solve some classical binary classification problem. We have 2 repositories, or 2 projects, and we take consecutive 50 lines and try to understand either these lines belong to project 1 or project 2. Our feature engineering pipeline should stand some requirements. The first 2 are devoted to filtering. We shouldn't process text files. We shouldn't process some unrelated source code, documents, auto-generated files. As you know, JavaScript libraries tend to be used in other projects, minified. We shouldn't analyze them as well. And the third and the fourth requirement means that we are small. Of course, the best way to operate on source code is using abstract syntax trees. It's the most robust way. But the problem with ASTs is that you have to write grammars for every language. And there are hundreds of languages throughout the world, and we just cannot afford writing grammars for everyone. So we should find a way to extract features from any source code files without much handwork. And our features should be as informative as possible. It means that you can, of course, you could take some prosodic features like length of lines, number of chars on every line, and so on and so forth, n-grams, whatever, but they're not going to be informative. So the first 2 requirements are successfully solved by Linguist project. It is being developed by GitHub itself. It's used for analyzing repositories and drawing these nice language bars. So your project is 50% C++, 30% Python, etc. The problem with Linguist is that it's written in Ruby and it's kind of slow, so we had to re-implement it from scratch using Go. It wasn't that much difficult because Linguist basically uses regular expressions. I think in some complex cases it tries to use some simple machine learning, but the number of these complex cases is not very big. Linguist supports more than 400 languages, which is really good. The last requirements are successfully solved for us by Pigments. It's a Python library which highlights source code. So it basically tokenizes your source code using regular expressions as well. It supports 400 languages too, but the problem is that only 50% intersects with Linguist. Anyway, 200 is still much, and it's OK. Pigment supports about 100 token types. I'll talk about token types, I think, on the next 2 slides. So this is what Pigments does. It highlights source code so that commands are gray, keywords are violet, strings are blue, and so on. The example from the previous slide is translated to this token stream. Every element of the stream is a pair. The first element of the pair is token type, and the second is token value. So we can see that first is token command single, it prints hello world. Then we have tags, keywords, names. So quite a few, actually 15 tokens for this small code abstract. The most evident way to convert this token stream to something useful for a machine learning engineer is, of course, one-hot encoding, where we take different token types and place one on the place of the occurring token type and zeros on all the other places. So this was our initial effort, and it worked. So I will continue with it. So we split our token stream into lines. Each line should contain no more than 40 tokens. It's more or less a technical constraint so that the stream is uniform. We merge indentations. And finally, we get about 200 dimensions after some clever handling of, for example, name styles, additional one-hot encoding there. We have about 8,000 features per line. But it's OK, because these features are very sparse. They can be efficiently encoding, and we have no problems with the memory. Finally, so that our neural network understands the stream OK, we apply mean dispersion normalization, of course, on the fly, because we have sparse structures. The problem with this approach is that one-hot encoding doesn't allow you to take the information from names occurring in the source code. As we analyzed all the GitHub data, all GitHub repositories, it's 18 million repositories, we found out that there are 15 million different names occurring in the source code. We cannot one-hot encode them, of course. And training like word-to-vec model on 15 million words is going to be hard. Anyway, we tried two approaches to using names. The first is Lsd Arm Sequence Modeling. You can view the presentation clicking on the link. I will talk about it in the end if I have time. And the second is ARTM topic modeling. ARTM is a best way, currently state-of-the-art way to do topic modeling. It's much better than LDA or Bayesian approaches. You can read about this in our blog. This picture denotes more or less how our neural network sees our features. So every line is 8,000 elements. But the black ones are, of course, zeros, and we have different colors for different token types. And it's not exactly what happens inside, but it should give you the main idea. It's like a mini-map. We apply some very common architecture of convolutional neural network. There are 4 convolutional layers and 3 fully connected layers. Nothing very special. The architecture was taken actually from image recognition. It worked OK in our case. The only thing we had to do is to tune the kernel size and pooling so that it works OK with our stream. This is some technical details about our neural network. So we use ReLU units, we use GD with momentum. It's very easy to write this because we use TensorFlow, and so everything is formalized well. This is our training pipeline, nothing special. We use TensorFlow for implementation, as I said, with Python 3, and of course we use NVIDIA GPUs. We do pre-processing on Spark because processing 18 million repositories is, kind of can take a long time. We store our database of features in cloud storage. It's more or less the same as Amazon S3. And since we use sparse matrices, we use normalization on the fly, of course. The results of our binary classification using our neural network is as follows. If you take Django and Twisted, both are web frameworks for Python, we get about 84% accuracy, which is much better than 50% if you throw a coin, of course. If you take some other projects, you take the similar, you have the similar accuracy. If you take projects written in different languages, you get really good accuracy, like more than 99%. And some Java projects also yield very good accuracy. We had other experiments, and if you summarize them, we get to the following conclusions: that neural network is likely to extract the internal similarity within the repository. It doesn't try to, compare the contents. It only works within a single repository. If the languages are different, it's very easy to do binary classification because there are different token types in some cases and different structure. So we believe that the neural network sees the source code as follows, more or less the same as a human does. So first we pay attention to highlighted tokens, class method, keywords. Then we extract some high-level features. We understand more. Then these high-level features go upper, and at last we understand the whole code abstract. Unlike deep neural network for images, we cannot visualize our kernel sufficiently because it's not image. We cannot get this picture for our source code. This is an open question. How can we get some introspection in what our neural network exactly learned? Oh. Okay. So we have 3 minutes left, and I'll cover some related work we do. The first is we try to cluster all the developers, but at this time, not using sophisticated features extracted by neural network, but only some metadata, so number of bytes written in each language, something else. And we use CUDA project. It's our own project. It's a k-means implementation using CUDA. It supports multiple GPUs. It supports FP16. It's very efficient. It allows you to cluster millions of samples in 10,000s of dimensions, like 1 hour. This is what we got after applying TSNE. So red dots are developers which we already contacted. Blue dots are all the developers on GitHub. So we basically contacted everybody except the outliers, which is good, I think. If we adjust our source code extraction pipeline a bit, we can extract information about indentation, so tabs and spaces. You may have heard about the article from Google, which focuses on tabs versus spaces, and we have, I think, more thorough research about this topic. You can view this interactive visualization of tabs and spaces, and the conclusion is that spaces rule, so most of the projects actually use spaces. And about ARTM modeling, so we extracted names from image repository and applied topic modeling and got some interesting results. We manually labeled 200 topics and found out, for example, that Windows API is similar to Pokemons or other funny things, or there are repositories related to pizza on GitHub. So you should check out the article. And finally, about Lsd Arm Sequence Modeling, we can try to sequence model the source code and get really smart code completion. So LSTM tries to understand you from few words and write all the code for you. While the code is syntactically correct, I think you can torture developers with it because it doesn't make sense sometimes at all. So all the words are OK, but if you summarize, it makes no sense. We think that we should try to elaborate on this topic more, because we think that, after all, if we use really good LSTMs, we can translate algorithm descriptions in natural language to source code, make a revolution, and fire like half of the software developers in the world. So this is all. Thank you.